Imagine a world where the vast, chaotic ocean of human knowledge is not only accessible but instantly organized, tailored just for you. A world where every fleeting question, every half-formed thought can be answered in milliseconds. This isn't science fiction, it's the digital reality we inhabit every single day. The journey of information, once a laborious trek through dusty library stacks and cumbersome card catalogs, now begins with the simple, elegant act of a single search. You type a few words, a fragmented idea, how do migratory birds navigate, or symptoms of the common cold, and in the blink of an eye, a perfectly ranked list appears. The most relevant, most authoritative, most useful information rises to the top, as if by magic. How does the machine know what you want? This magic extends beyond search. When you finish a movie, a streaming service suggests your next favorite film, often before you even know what you're in the mood for. A music app curates a playlist that seems to read your mind, capturing the exact vibe you were feeling. An online store shows you products you didn't even know you needed, yet they feel perfectly suited to your tastes. It's a constant, subtle conversation between you and the digital world, a system that seems to understand you intimately. And then there's the magic you don't see. Every day a silent guardian stands watch over your inbox, deflecting a relentless barrage of junk mail, phishing attempts, and unwanted noise. It sorts, categorizes, and protects, ensuring that the messages that matter are the ones you see. This invisible shield is perhaps the most underappreciated marvel of our online lives. What if I told you that for decades these seemingly disparate experiences, search, recommendation, and filtering, were all powered by the same fundamental principle? That a single, elegant, and surprisingly simple mathematical idea formed the bedrock of the modern internet as we know it? For years, one algorithm was the ghost in the machine, the invisible architect shaping how we find, consume, and organize information. That algorithm is called TF-IDF, term Frequency Inverse Document Frequency. It might sound complex, but at its heart is a beautifully intuitive concept. A concept born not in the age of silicon and smartphones, but in the era of punch cards and mainframe computers. Its development, spearheaded by pioneers like Gerard Salton at Cornell University with his groundbreaking smart information retrieval system in the 1960s, was a quantum leap. Salton and his contemporaries asked a simple question: how can we teach a machine to determine which documents are most relevant to a query? Their answer didn't involve understanding language, but rather, counting words. TF-IDF operates on two simple principles. First, term frequency. The more often a word appears in a document, the more important it likely is to that document's topic. If the word galaxy appears 20 times in an article, that article is probably about astronomy. Second, inverse document frequency. The more documents a word appears in across a whole collection, the important it is as a unique identifier. Words like the, a, and is appear everywhere, so they tell us very little. TF-IDF brilliantly combines these two ideas. It gives high scores to words that are frequent in one document but rare everywhere else. It finds the unique descriptive terms that truly define a piece of text. And for a long time, this was enough. It was revolutionary. TF-IDF built search engines, powered news aggregators, and fought off spam. It was the workhorse of the information age, but it had a fundamental, unshakable limit. TF-IDF is a mathematician, not a linguist. It can count, but it cannot comprehend. It has no concept of meaning, context, or nuance. To TF-IDF, the words king and queen are as different as king and cabbage. It doesn't understand that running a company and managing a business are synonymous. It can't detect sarcasm, irony, or the subtle shades of human expression. It sees a document as nothing more than a bag of words, their rich semantic relationships completely lost. This bag of words problem created a ceiling. As our demand for more sophisticated, more human-like interaction with technology grew, the cracks in the foundation began to show. Search results could be gamed, recommendations could feel shallow. The need for true comprehension became undeniable. Data scientists and engineers were forced to ask a new question. How do we move beyond simply counting words and start understanding their meaning? This question sparked a new revolution, leading to the development of technologies that can grasp the intricate web of relationships between words, concepts, and ideas. In this series, we will journey through the entire story of information retrieval. We will start at the beginning, exploring the genius of TF-IDF and its variations. We'll get our hands dirty, writing Python code to see exactly how it works and where it excels. We will examine its real-world triumphs in case studies from spam filtering to document classification, but we will also push it to its breaking point, demonstrating its inherent limitations, and from there, we will venture into the new frontier of natural language processing, discovering the powerful embedding models that are defining the future, and finally teaching machines not just to count, but to understand. The story of TF-IDF is the story of our quest to organize knowledge itself. A story of brilliant successes, frustrating limitations, and the relentless drive to evolve. Simplicity, easy to calculate. Interpretability, you can explain why a word is important. Works across search, classification, sentiment analysis, show how it became the backbone of early search engines. For all its elegance and power, TF-IDF is not a silver bullet. It was a monumental leap, a testament to the genius of pioneers like Gerard Salton and Karen Spark Jones. Their work laid the foundation for modern information retrieval. However, the very design that made TF-IDF so effective and computationally feasible in its time also contained inherent limitations. These aren't bugs or errors in the algorithm, they are fundamental cracks in its foundation, consequences of its core assumption, the bag of words model. To truly appreciate the revolution that came next, we must first understand the challenges that TF-IDF, for all its strengths, simply could not overcome. Let's peel back the layers and examine the cracks in this brilliant but ultimately incomplete system. The first and most profound limitation is the bag of words problem. TF-IDF at its heart treats a document like a sack full of words. It meticulously counts each word and assesses its rarity, but it completely ignores the order, the grammar, the syntax, the very structure that gives language its precise meaning. In the world of TF-IDF, the sentence, "the dog bit the man and the man bit the dog" are computationally identical. They contain the exact same words, so they receive the exact same vector representation. To the algorithm, these two vastly different events are indistinguishable. This isn't just a quirky edge case, it's a fundamental failure to capture meaning. Consider a search query like, "how to not get a parking ticket." A TF-IDF-based system might strip away the "not" as a common stop word or simply treat it as another token in the bag. It could easily return the most relevant document for "how to get a parking ticket," the exact opposite of the user's intent. This loss of sequential information means that negation, causality, and complex relationships are lost in translation. The algorithm sees the words, but not the music of the language. This single issue is the parent of many of TF-IDF's other challenges, including its blindness to context. This leads us to the problem of context blindness, or polysemy. Many words have multiple meanings, and their interpretation depends entirely on the surrounding words. TF-IDF has no mechanism to handle this. The word apple is a classic example. In the sentence, "I am eating an apple," it's a fruit. In "I am coding on my apple," it's a technology company. For a human, the distinction is effortless, but for TF-IDF, apple is just apple. It's a single dimension in the vector space, a single entry in the vocabulary with a single IDF score. The algorithm is blind to the contextual clues that differentiate the fruit from the corporation. This ambiguity can have serious consequences. Imagine a news classification system trying to sort articles. It might lump a story about a financial market crash in with reports of a car crash, or consider the word bank. Is it a riverbank or a financial institution? Crane, a bird or a piece of construction equipment? Java, a coffee bean or a programming language? Without context, the model is flying blind, leading to inaccurate search results, flawed topic modeling, and unreliable classifications. It's a system that understands words as symbols, but not as carriers of meaning. Closely related to context blindness is the problem of synonymy. If polysemy is one word with many meanings, synonymy is many words with one meaning. Humans know that car and automobile refer to the same thing. We understand that big and large or quick and fast are interchangeable in many contexts. TF-IDF does not. In its vector space, car and automobile are treated as two completely different, unrelated words. They become separate dimensions. A document that uses the word car 10 times will have a high value on the car dimension, but 0 on the automobile dimension. This is known as the vocabulary mismatch problem. A user searching for car maintenance tips will completely miss the perfect document titled "An Expert's Guide to Automobile Care." This leads to poor recall. The system fails to retrieve relevant information simply because the user and the document author chose different synonyms. Early attempts to fix this involved manually expanding queries using a thesaurus like WordNet. but this was a brittle solution, often introducing more noise than signal, especially when dealing with polysemous words. The core issue remained: the model had no underlying concept of semantic similarity. Let's make this concrete with a simple demonstration in Python. Here we'll use the popular scikit-learn library to see these limitations in action. First, we import the FID vectorizer. Now let's define a simple corpus to demonstrate the bag of words problem. These sentences have opposite meanings. We create a vectorizer object and use it to transform our corpus into a TF-IDF matrix. When we print the resulting vectors, look at this. They are identical. The algorithm sees no difference. Now let's test synonymy. Our new corpus will fit and transform this. If we inspect the vocabulary the vectorizer has built, we see car and automobile are indexed as two different features. They are treated as completely unrelated terms. A query for car would find zero similarity with the second sentence. Finally, let's look at polysemy. The vectorizer creates a single feature for the word apple. It has no way of knowing that the apple in the first sentence is a trillion-dollar company, and the apple in the second is a piece of fruit. This simple code clearly illustrates the theoretical cracks we've been discussing. They are not abstract concepts, they are practical barriers to understanding language. Beyond these semantic gaps, TF-IDF faces practical operational challenges. One of the most significant is its struggle with the evolution of language. Language is not static, it's a living, breathing entity that changes daily. New slang, acronyms, hashtags, and technical terms are constantly emerging, especially online. Words like Riz or finna go from obscurity to ubiquity in weeks. When these new, out-of-vocabulary words appear, a pre-trained TF-IDF model has no idea what to do with them. They are simply ignored, discarded as noise. This means any system relying on TF-IDF for real-time analysis like social media trend monitoring or brand reputation management is always a step behind, unable to capture the latest linguistic currency. Another major crack appears when we consider scale. The I in TF-IDF, inverse document frequency, is the algorithm's secret sauce, but it's also an Achilles heel. A word's IDF score is calculated relative to the document collection. This is fine for a static, unchanging corpus, but what about a real-world system like a news aggregator or a web search index where thousands of new documents are added every minute? Each time a new document is added, the document frequencies of potentially thousands of words can change. To maintain accuracy, you would need to recalculate the IDF scores for the entire vocabulary across the entire corpus. For a corpus of billions of documents and a vocabulary of millions of words, this is computationally prohibitive. It's like having to reread every book in the Library of Congress every time a new pamphlet is published. The common workaround is to calculate IDF scores on a large, fixed, representative corpus, and then use those static scores for new documents. But this is a compromise. The scores become stale and less representative of the specific documents being processed, slowly degrading the model's performance over time. Finally, there's a subtle but perverse quirk in the logic of inverse document frequency. It can give undue importance to meaningless rarity. The core assumption is that rare words are more significant. But is that always true? Consider a typo. A word misspelled in a unique way will appear in only one document out of millions. This gives it an astronomically high IDF score. A search query containing that same typo could mistakenly rank that document as the single most relevant result. Similarly, rare identifiers, product codes, or random strings can be massively overweighted, drowning out the signal from more common but contextually important terms. This vulnerability has been exploited in areas like spam filtering. Spammers would intentionally pepper their emails with bizarre, rare words, a practice known as word salad, to try and fool TF-IDF-based filters. The filter would see these high IDF words and might misclassify the email as unique and important rather than junk. The model's simplistic definition of importance, rarity, becomes a bug that can be exploited. Word order, context, synonyms, scalability, and the very definition of importance. These are the cracks in the system. While variations and patches were developed to mitigate some of these issues, they were ultimately just bandages on a fundamentally limited model. The world of natural language processing needed a new paradigm. It needed a way to represent words not as isolated, discrete units, but as points in a rich, meaningful space, a space where synonyms are close together, where context can shift a word's position, and where the complex relationships of language can finally be captured. The stage was set for the embedding revolution. Delta TF-IDF adapts for tasks like authorship attribution. CF-IDF works with classes categories instead of whole corpora. TF-IDF plus LDA, hybrid methods for topic modeling. Tweaks kept it alive, but the limits were structural. Word 2, vec, glove, FastText. Words live in vector space, capturing meaning. King, man plus woman, queen analogy. TF-IDF =, counts words. Embeddings =, understands words. Show how embeddings solve synonym/polysemy/ context issues. Still used in scikit-learn pipelines, often combined with embeddings. Great baseline for classification tasks. Think of it as the calculator of text analysis, fast, reliable, but not the whole picture anymore. TF-IDF built the internet we know today. From the earliest search engines to the first document classifiers, its simple elegance powered the information revolution. But like any foundational technology, its blind spots, its inherent limitations, forced us to evolve. We move towards the nuanced world of embeddings and beyond. Understanding the limits of TF-IDF isn't about discarding a relic of the past, it's about appreciating the crucial stepping stones, the ingenious first principles that led directly to the sophisticated artificial intelligence we interact with every single day. So what made it so powerful? At its core, TF-IDF provided a brilliant solution to a fundamental problem. How can a machine determine which documents are most relevant to a query? Imagine a library with millions of books. If you ask for a book about dragons, you don't want a book that mentions the word dragon once in a footnote. You want the book dragons. TF-IDF automates this intuition. It quantifies relevance. It looks for words that are frequent in a specific document but rare across all other documents. That combination is the magic signal for importance. This simple idea allowed early search engines to crawl the burgeoning web and return surprisingly relevant results, transforming a chaotic mess of data into a navigable universe of information. To truly appreciate this, we have to go back in time, before the web, to the 1960s. The world was drowning in a different kind of information explosion. Scientific papers, legal documents, intelligence reports. The challenge was the same, finding the needle in the haystack. This is where we meet Gerard Salton, a pioneer in computer science. At Cornell University, Salton and his team developed the Smart Information Retrieval System. SMART, which stands for Salton's Magic Automatic Retriever of Text, was a groundbreaking project. It was here that the vector space model was born. The idea that documents could be represented not as strings of text, but as numerical vectors in a high-dimensional space. And the key to weighting the elements of these vectors, the concepts that would evolve into TF-IDF, they were laying the groundwork, building the mathematical language that would allow us to have conversations with vast archives of text. Let's break down the name, TF-IDF. It stands for Term Frequency Inverse Document Frequency. It sounds complex, but the two parts are beautifully simple. First, term frequency, or TF. This is just what it sounds like. How often does a term appear in a single document? If the word galaxy appears 10 times in a 100-word article about space, its term frequency is high. This is our first clue that the article is probably about galaxies. But frequency alone is misleading. Common words like the, a, and is will have a high frequency in almost every document, but they tell us nothing about the topic. They're just noise. This is where the second part, inverse document frequency or IDF, comes in. It's the counterbalance. IDF measures how common or rare a word is across the entire collection of documents, or corpus. A word like the will appear in almost every document, so its IDF score will be very low, effectively penalizing it. But a word like quasar might only appear in a handful of specialized astronomy papers. Its rarity gives it a high IDF score, marking it as a significant topic-defining term. TF-IDF is simply the product of these two scores. A term gets a high TF-IDF weight if it appears frequently in one document, high TF, but rarely in all the others, high IDF. It's the perfect mathematical signature for a keyword. Theory is one thing, but let's see this in practice. Here I have a simple Python environment and the popular library. We'll create a tiny corpus of 3 documents. Document 1, the cat sat on the mat. Document 2, the dog chased the cat. Document 3, the dog and the bird are friends. Now we'll use S. With just a few lines of code, we can instantiate the vectorizer and ask it to transform our text documents into a TF-IDF matrix. And here's the result. It's a matrix of numbers. Each row represents one of our documents, and each column represents a unique word from our vocabulary: cat, dog, mat, chased, and so on. The values in the cells are the TF-IDF scores. Notice how words like "the" have been automatically assigned low scores or even ignored, while a word like "mat," which only appears in the first document, gets a high score for that document. This matrix is now a machine-readable representation of our text. We can use it to calculate similarity between documents or to see how well a document matches a search query. This simple mechanism has been the backbone of countless real-world applications. Consider spam filtering. Early spam filters relied heavily on TF-IDF. They were trained on thousands of spam and non-spam emails. The algorithm quickly learned that words like Viagra, free, offer, winner, and guarantee had a very high TF-IDF score in spam emails but not in legitimate ones. When a new email arrived, it was converted into a TF-IDF vector, and if its vector was mathematically close to the typical spam vector, it was flagged. Another classic example is news classification. Imagine a news aggregator that needs to sort thousands of incoming articles into categories like sports, politics, and technology. By analyzing a labeled dataset, a TF-IDF-based model can learn that articles with high scores for touchdown, playoffs, and quarterback belong in sports, while those with high scores for election, Senate, and bill belong in politics. It's a powerful and computationally cheap way to bring order to chaos. But for all its power, TF-IDF has a fundamental, unavoidable flaw. It's a bag of words. It sees text as an unordered collection of terms. It has no concept of grammar, no understanding of context, and absolutely no grasp of meaning, what we call semantics. This leads to several major problems. First, it can't handle synonyms. To a TF-IDF model, the words car, automobile, and vehicle are as different from each other as car and banana. A search for automobile won't find a document that only uses the word car. This is a huge limitation. Second, it's blind to polysemy. Words with multiple meanings. The word bank in riverbank and investment bank are treated as the same token, muddying the semantic waters. And then there's the issue of nuance, sarcasm, and negation. The sentences, "this movie was good" and "this movie was not good" are seen as highly similar by TF-IDF because they share most of the same words. The crucial meaning-inverting word "not" is often discarded as a stop word or given a low IDF score. The model misses the entire point. This is where the simplicity of TF-IDF becomes its Achilles heel. Researchers were well aware of these limitations, and for decades they worked to improve upon the basic formula. This led to a whole family of TF-IDF variations. For instance, there's Delta TF-IDF, which was designed to be more effective for information extraction tasks. There's CF-IDF, or class frequency-based IDF, which adjusts the term weight based on its frequency within a specific class of documents, making it better for text classification. And there are others, like DF-ICF, which tries to find the most discriminative terms to distinguish between categories. Each of these was a clever tweak, an attempt to patch the holes in the original model and squeeze out more performance for specific tasks. They represent the ongoing effort to make word counting smarter, but they were all ultimately bound by the same bag of words constraint. The real breakthrough required a complete paradigm shift. We had to move from counting words to understanding their meaning. This is the leap to word embeddings. Instead of a sparse vector with tens of thousands of dimensions where most values are 0, embeddings represent words as dense, low-dimensional vectors, say 300 dimensions instead of 50,000. But the magic isn't just the size reduction, it's what those dimensions represent. They capture semantic relationships. In an embedding space, words with similar meanings are located close to each other. Car and automobile would be neighbors, but it goes deeper. The between words are encoded as directions in this space. The vector from man to woman is remarkably similar to the vector from king to queen. This allows for a kind of vector arithmetic. King, man plus woman results in a vector very close to queen. This is true semantic understanding, something TF-IDF could only dream of. Let's go back to our code, but this time, we'll compare TF-IDF with a pre-trained sentence embedding model. Our query will be, a vehicle that runs on rails. Now let's search our documents. TF-IDF sees no overlap. None of the words vehicle, runs, or rails appear in our original documents about cats and dogs. From its perspective, the relevance is 0. It returns nothing. Now let's run the same query through an embedding model. The model converts our query into a single vector representing its meaning. It also converts each of our documents into a vector. Then it calculates the cosine similarity, a measure of how close these vectors are in the high-dimensional space. Even though the document, "The dog chased the cat," doesn't share any keywords, an advanced model might pick up on the faint semantic scent of chased relating to runs. But let's use a better example document. The train arrived at the station. TF-IDF would fail our query. But the embedding model knows that vehicle that runs on rails is semantically very close to train. It will return the train document with a high similarity score. This is the power of understanding context over just counting keywords. And so we come full circle. TF-IDF, born from the necessity of organizing physical documents, built the digital information architecture we know today. But its inherent blind spots, its inability to grasp meaning, forced us to evolve into the richer, more nuanced world of embeddings and the large language models they power. Understanding its limits isn't about discarding it. In fact, for many simple classification and search tasks, TF-IDF is still incredibly fast, efficient, and effective. It's about appreciating the journey, recognizing the brilliant stepping stones that led from Gerard Salton's smart system to the generative AI of today. It's a testament to human ingenuity, a story of building ever more sophisticated ways to communicate with our own knowledge. The journey, of course, doesn't end here. The world of embeddings is vast and fascinating, from Word2Vec and Glove to the transformer-based models like BERT that power modern search. If you want me to do a deep dive into the mechanics of embeddings, the different types of topic modeling like latent Dirichlet allocation, or even explore the future beyond embeddings and what might come next, let me know in the comments below. Your feedback guides the content on this channel. Thanks for watching.